Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series called Happily Ever After. In this show, we learn how to diagnose the air buckle from other buckle types and then eliminate it by pegging a knob, or in some cases strengthening a knob first and then pegging it. Those of you who follow my work will have heard me say many times that a wrinkle's not a wrinkle's not a wrinkle, because there are about 20 common types. Each has its own name, diagnostics, and remedies. The same is true of core crush. There are 3 types. One is a tight defect, another is a loose defect, and another still is not even a winding defect at all. It is a product process design issue. Last week, we covered 2 of the most common types of telescope. In this show, we cover 1 of the half dozen or so types of buckles. As is usually the case, we get started by knowing what to look for. In the case of the types of buckles or stars, they may look like wavy layers or spokes. The distinction is not important because that is simply an artifact of perception rather than occluded diagnostics. Instead, we look for symmetry or lack of symmetry in the angle between the spokes and whether the spokes favor one end of the roll and not the other. Once we have trained our eyes to see the salient features of buckles and stars, then we can diagnose type. Here is a list of the common types. We will not discuss them here because they are given in great detail in the advanced winding section of my award-winning and trademark Web 101 class that has been taken by 5,000 students. Instead, we will only focus on one type, the air buckle. The appearance of the wound roll is a relatively uniform series of CD-oriented buckles wrinkles. If the buckles are not uniform, the problem is likely excessive thickness variation profile of one or more of the components of the structure. The buckles favor the area just above the core and never extend to the outside, as is true of all buckle types. With some products, such as laminates with low green tack adhesives, the web may delaminate at those CD buckles. Other factors that must be present for this defect is that the webs must be smooth and not thick. They also must be wound at higher speeds, say faster than 100 meters per minute, for reasons we will cover next. Finally, the defect does not manifest immediately. Rather, it takes something like an hour to a day to develop. The mechanics are pretty straightforward. Air is entrained into the winding roll, as guaranteed by the laws of physics that are somewhat similar to the air entrained between a web and a roller. This is true whether you have a pure center wind or have a nip roller. Obviously, a nip roller will exclude much more air. However, the air between the layers is free to leak out the side of the roll, something like a slow leak in a car tire. The air that had supported the web, and now that support is lost, so that the inner layers will collapse under pressure from the layers above. If you want to see the leak, you could immerse your wound roll in a water tank and you would see tiny bubbles developing on the end of the roll. Aside from dunking your roll in a water tank and all of the visual observations, you can check your working theory of the mechanics by doing trials that look at time, the TNTs of winding, and web thicknesses. Slowing down is not only a test, but it's also one extremely powerful remedy, though one not usually favored by your boss. If slowing down is not allowed by the boss, then your only strong alternative is to reduce the amount of air being entrained by an effective nip roller. That is a chapter-long discussion in itself and one we can't cover here. As a practical matter, we will start by increasing nip load in increasing amounts until the problem is resolved or we develop a new problem that must be solved first. So, start by pegging the air pressure on the nip roller cylinder. That would be perhaps 5 or more bar in most plants. If that doesn't do it, you can increase supply pressure even more with an air-over-air intensifier, a simple upgrade that should get you to maximum design pressure of the cylinder, which is often about 8 bar. Though you should see some progress already by virtue of less buckling, it might not be enough. It is common for many film winders in particular to have undersized nip loading systems. You may need bigger cylinders. Another problem I've encountered is crushing cores with the effort. In my mind, I'm quite happy because it shows we are doing something to increase the winding tightness, and the solution to that problem is quite simple: larger core wall thicknesses. My experience with, say, 10 cases of air buckles is that doing all of the above things will kill the buckles. However, I had one case where all of the above did not solve the problem. I have no idea why, but that doesn't change how I would approach the air buckle problem. Thank you so very much for letting me share stories from the field. Stay tuned for next week, where we will again show how to annihilate air buckles, but with a different knob. If you have a topic you would like to hear about, let me know in the comment section below. If you found any of these stories to be interesting or useful, please like and share and subscribe. And remember to check out the show notes for surprises. See you next time.